Brian Greene and Leonard Susskind, Quantum Mechanics, Black Holes and String Theory. Journey through literary realms and immerse yourself in words. Lose yourself in the captivating world of literature with our Brian Greene and Leonard Susskind Quantum Mechanics, Black Holes and String Theory articles. From book recommendations to author spotlights, we'll transport you to imaginative realms and inspire your love for reading. Holes, Quantum Leonard and Brian Black Greene Theory, String Susskind Mechanics and Brian Greene and Leonard Susskind Quantum Mechanics, Black Holes and renowned physicist and pioneer of string theory, Leonard Susskind talks with Brian Greene about some of the biggest breakthroughs in physics. Listen to their wide-ranging conversation. Brian Greene and Leonard Susskind, Quantum Mechanics, Black Holes and String Theory. Quantum complexity inside black holes. Leonard Susskind, YouTube. Brian Greene and Leonard Susskind, Quantum Mechanics, Black Holes and String Theory. Brian Greene and Sir Roger Penrose. World Science UQ. A Session Views. Brian Greene and Andrea Ghez. The Hunt for Supermassive Black Holes Views. Published theoretical physicist and science popularizer Brian Greene presenting at the World Science Festival. Image credit. World Science Festival. Greg Kessler, Brian Greene. Niels Bohr and a generation of intrepid explorers ventured deep into the microrealm, where they encountered quantum mechanics, an enigmatic theory formulated with radically new physical entanglement, black holes, and wormholes. An informal discussion with Brian Greene and Leonard Susskind. Quantum Mechanics, Black Holes and String Theory. Brian Greene and Sir Roger Penrose. World Science UQ. A Session. Brian Greene and Leonard Susskind. Quantum Mechanics, Black Holes and Niels Bohr and a generation of intrepid explorers ventured deep into the microrealm, where they encountered quantum mechanics, an enigmatic theory formulated with radically new physical are groping toward a quantum theory of gravity by Leonard Susskind. 52 Scientific American, April 1997. Black holes and the information paradox. Black hole's surface looks to windbag in the spaceship like a spherical membrane called the horizon. Windbag sees Goulash, who is falling into the black hole, as being slowed down, and high school students around the world bring your curiosity and your questions for a live Q&A with Brian Greene covering black holes, time travel, the Big Bang, the multiverse, and whatever else and wherever else your imagination soars. For this Emma, the sky is surely not the limit. Download Leonard Susskind on String Theory and Black Holes. 7 books are groping toward a quantum theory of gravity by Leonard Susskind. 52 Scientific American, April 1997. Black holes and the information paradox. Black hole's surface looks to windbag in the spaceship like a spherical membrane called the horizon. Brian Greene and Leonard Susskind. Quantum Mechanics, Black Holes and String Theory. Renowned physicist and pioneer of string theory, Leonard Susskind talks with Brian Greene about some of the biggest. Brian Greene. Black holes. Albert Einstein. Quantum mechanics. With his general theory of relativity, Einstein illuminated the string theorist, mathematician and theoretical physicist. Brian Greene talks about black holes, quantum gravity and the possibility black holes warp space and time, squeeze matter to a vanishing point, and trap light so that it cannot escape. Black holes. With 35 years ago, string theory took physics by storm, promising the coveted unified theory of nature's forces that Einstein. In this thought-provoking video, renowned theoretical physicist Brian Greene delves into the complexities of string theory, and it's when the theoretical physicist Leonard Susskind encountered a head-scratching paradox about black holes. He turned to, and Sean Carroll joins Brian Greene for a conversation spanning the quantum to the cosmos, teeing up their live event in Nick on. Brian Greene moderates this fascinating program exploring the fundamental principles of quantum physics. Anyone with a note. Audio clears up at the 8:20 mark. Part 1 of a conference lecture given by Leonard Susskind on holographic cosmology. Conclusion. Taking everything into consideration, it is clear that the post delivers valuable insights concerning Brian Greene and Leonard Susskind quantum mechanics, black holes and string theory. From start to finish, the writer illustrates a deep understanding on the topic. Notably, the section on why stands out as a highlight. Thanks for reading this post. If you have any questions, feel free to contact me through the comments. I look forward to hearing from you. Additionally, below are some similar articles that you may find interesting. Related image with Brian Greene and Leonard Susskind, Quantum Mechanics, Black Holes and String Theory. What is this page? This page lists the scientific contributions of an author, who either does not have a ResearchGate profile, or has not yet added these contributions to their profile. It was automatically created by ResearchGate to create a record of this author's body of work. We create such pages to advance our goal of creating and maintaining the most comprehensive scientific repository possible. In doing so, we process publicly available, personal data relating to the author as a member of the scientific community. If you are a ResearchGate member, you can follow this page to keep up with this author's work. If you are this author and you don't want us to display this page anymore, please let us know. Publications 292. Complexity of parallel parking a unicycle as a function of the distance. Conjectured complexity. See document class 12 PT minimal. Universality in long distance geometry and quantum complexity. Article. Full text available. October 2023. Adam R. Brown. Michael H. Friedman. Henry W. Lynn. Leonard Susskind. In physics, two systems that radically differ at short scales can exhibit strikingly similar macroscopic behavior. They are part of the same long-distance universality class. Here we apply this viewpoint to geometry and initiate a program of classifying homogeneous metrics on group manifolds by their long-distance properties. We show that many Site. Download full text. Figure 1. The left panel shows the Penrose diagram for de Sitter space. Figure 2. A T-slice of ds and the stretched horizons shown as light. Figure 6. The entropy deficit as a function of x. Figure 7. The inside-out transition as seen by an observer in the 1. Figure 8. Time scales for the inside-out process. The short blue. Black holes hint towards de Sitter matrix theory. August 2023. De Sitter black holes and other non-perturbative configurations can be used to probe the holographic degrees of freedom of de Sitter space. For small black holes, evidence was first provided in the seminal work of Banks, Fiel, and Morais and follow-ups by Banks and Fischler, showing that ds is described by a form of matrix theory. For large black, Figure 1. Chords are represented by x. The number of chords is. Figure 4. A mass close to the Planck mass in three-dimensional de Sitter. Figure 5. A vertex for the case Q6. Figure 6. The simplest vacuum melon diagram. 9. Figure 7. Additional vacuum diagrams. A. Another melon diagram. B. A. De Sitter space has no chords. Almost everything is confined. Preprint. This paper describes a phenomenon in which all but a tiny fraction of the fundamental holographic degrees of the SiC theory are confined, as in quark confinement in the double-scaled infinite temperature limit. The mechanism for confinement is an essential ingredient in the duality between SiC and de Sitter space. The mechanism, which removes L. In Brown et al. PRX Quantum, TBA, 2023, we discuss how holographic quantum gravity may be simulated using quantum devices, and we give a specific proposal: teleportation by size and the phenomenon of size winding. Here, we elaborate on what it means to do quantum gravity in the lab and how size winding connects to bulk gravitational. Fig. 4. A short summary of teleportation by size, discussing different quantum gravity in the lab. Teleportation by size and traversable were. With the long-term goal of studying models of quantum gravity in the lab, we propose holographic teleportation protocols that can be readily executed in tabletop experiments. These protocols exhibit similar behavior to that seen in the recent traversable wormhole constructions of Gao et al. J. High Energy Phys. 2017, 151, 2017 and Maldacena et. The Gauhier-Kleban-Susskind no-go theorem says that the symmetry of de Sitter space is incompatible with finite entropy. The meaning and consequences of the theorem are discussed in light of recent developments in holography and gravitational path integrals. The relation between the GKS theorem, Boltzmann fluctuations, wormholes, and exponentially the Gaussian-Kleban-Susskind no-go theorem says that the symmetry of de Sitter space is incompatible with finite entropy. The meaning and consequences of the theorem are discussed in the light of recent developments in holography and gravitational path integrals. The relation between the GKS, the Gaussian